Thank you so much. Thank you for the invitation to speak here today. I've heard such great things about this event over the years, and it's great to finally be at one. I'm going to talk about explicit R equal TV or rank bounds, and I have to thank Patrick for his fantastic talk right ahead of mine, because he said almost all the words that I was hoping to not define carefully for you, and then define them carefully for you. So thank you. So in the title, we're going to hear a little bit more about what these R equal T theorems are. The word explicit is just a signal that we're going to be working in a very specific setting. So I decided to talk about this project partly because of the computational aspects. I think it fits in nicely with some of the themes of the summer school. So we're going to limit ourselves to a very specific situation. And then the via rank bounds is going to be this new strategy for proving these types of modularity theorems that's going to take the role of Weil's numerical criterion. So we'll talk about that when we get there. So fundamentally, everything I'm talking about is joint with the same Preston Wake and Carl Wong Erickson. I call them WWE in my head. So I know. When I was a grad student, I was like, what would WWE say? And so at the core, like the main theme of my talk today is trying to highlight the beautiful relationship between modular forms and arithmetic. So the project with Carl and Preston, it's a series of 2 papers. The first paper focuses more on the deformation theory part of the project, and the second paper is all about computation. So my goal is to actually talk about both papers and highlight the computation throughout. Sounds good? All right, so we're actually going to start at the end of Patrick's talk. He mentioned the Herbert-Ribet theorem, so we'll make it precise now. So this is a very famous result that says the following. So let P be an odd prime. We want to define the following. So A is going to be the P CELO subgroup of the ideal class group of the P cyclotomic field. So this is the same ideal class group that was defined before. And then we have our group of the cyclotomic field, which is isomorphic to Z mod P Z cross. And we can look at the character group, or define the character group as well, of G as follows. So omega is our mod P cyclotomic character. So as Patrick discussed, we have an action on this class group. And so we can view A as a ZPG module. And it gives us this nice decomposition where we have our parts corresponding to this action. So the epsilon I is an orthogonal idempotent associated to each character in this character group. So the Herbert-Ribet theorem says the following. It says, let I be odd between 3 and P minus 2, including 3 and P minus 2. Then the corresponding part of our P CELO subgroup of the ideal class group is non-zero if and only if P divides the P minus 1 Bernoulli number, where B to the K is the kth Bernoulli number. So I always like to point out with this if and only if that there were many years between the 2 directions. So in the forwards direction, this was proven in 1932 by Herbrandt. And the reverse direction was not until 1976 by Ribet. So you can think of that when you're trying to prove your if and only if statements. 40 years. And in fact, the paper of Ribet just celebrated its 50th birthday. I just came back from the birthday party for this paper. I'd never been to a birthday party for a paper before. Someone asked me, I told my kickball team this, and someone asked if there was cake, and I felt very sad that there was not. But Patrick a little bit spoiled the surprise that this theorem has to do with modular forms. So as written, you would not necessarily think it has to do with modular forms. But for Ribet's converse statement, it actually touches on 6 major facets of number theory. So I encourage you, if you have not, to go find this really wonderful paper of Mazur that's explaining this other paper of Ribet. And so I will steal from Mazur the circle of Mazur. So you might have seen it before. It's going to walk us through the proof of this Herbert-Ribet theorem. So this theorem, there's going to be 6 boxes that appear. And my goal is to tell you what each box is, and then tell you the connection to the previous box. Okay? So the 2 boxes that appear in the statement of the Herbert-Ribet theorem are ideal class groups, specifically of these cyclotomic fields, and Bernoulli numbers. Okay, and so the forwards arrow here, this is Herbrandt's theorem, and that follows just from classical algebraic number theory. We don't need a ton of extra machinery. All right, and so for box 2, we have our Bernoulli numbers. So let me see if I can write this on the board for us. Good, juicy marker. Okay, so the 2kth Bernoulli number, we have minus 1 to the k plus 1 times 2 times 2k factorial over 2 pi to the 2k times our Riemann zeta value at 2k. and this is for k at least 1. So that's a Bernoulli number. It's closely related to the Riemann zeta values. All right, and so what's our next facet going to be? Came up very briefly, although this is what Patrick was not talking about, right? So the next facet are our Eisenstein series. So these are maybe the first example of modular forms that you might come across when you're studying modular forms. You can write down very nice cube expansions for them, which have come up. And so in particular, the connection between them is that the Bernoulli numbers show up in their constant terms, right? And so the Bernoulli numbers are very closely related to these Eisenstein series. Okay, so now here's where we go a little further around the circle. Okay, so what's our next stop going to be? Well, if you think about modular forms, we can break them down into our Eisenstein series and our Cuss forms. And so our next stop are our Cuss forms. And so what's the relationship here? Well, I'm getting all confused with my arrows. So if we have p divisibility by a Bernoulli number, that's telling us that our constant term of the Eisenstein series is going to vanish mod p. And that's going to give us a congruence with a Cuss form. So our arrow here between 3 and 4 is corresponding to a congruence existing between an Eisenstein series and a Cuss form. And so this is a very interesting question. So when we talk about congruences between modular forms, the setup's exactly what Patrick outlined, except throughout this talk, we're always going to fix one of the modular forms to be an Eisenstein series and one to be a Cuss form. And so when we think about congruences, I just want to point out that there's two directions we can ask about, right? We can say, here's a characteristic zero modular form. Is there another one that's congruent mod p? And we can also ask, if you have a Q expansion mod p, so in characteristic p, can you lift it to a characteristic zero modular form? And those are both very important questions. All right, so what's our next stop on the circle? Okay, so we have Cuss forms. So what's next? Does anyone have a guess? Have you seen the paper? Okay, we're not in the guessing mood. All right, so Galois representations are our next stop. This came up briefly again in the previous talk. I had started writing in my notes like, Patrick mentioned this, and all my notes are covered. So given a Cuss form with certain properties, we can attach a Galois representation to it. And so you can think of a Galois representation as being a homomorphism, perhaps from the absolute Galois group into like GL2 of either a finite extension of ZP, if we're working in characteristic 0, or if we reduce modulo prime, then we might look at a finite extension of FP, for example. And so what's the connection here? Well, again, we have two directions to consider. So Eichler, Shimura, Deligne, Sarah and Deligne gave a way to construct a Galois representation that's attached to a Cuss form. So that's the direction we're given a Cuss form, and we want to attach a Galois representation. And then in the reverse direction, we can say, okay, given a Galois representation with certain properties, for example, maybe odd, irreducible, two-dimensional, can we find a Cuss form that it came from? So this is the idea of modularity, right? Does every Galois representation with certain properties come from a modular form? So this was one of the key inputs in the proof of Fermat's last theorem, showing that all of our Galois representations with certain properties do in fact come from a modular form. Okay, so that's that arrow. And then our last box here are abelian extensions of cyclotomic fields. So my understanding is that you all studied cyclotomic fields in one of the mini courses. And so we're going to be looking at various abelian extensions of them in the talk. And so a Galois representation will cut out some sort of number field. And so part of the rivet wrench, which I like the imagery of that, right, is constructing Galois representation and corresponding abelian extension cyclotomic fields that have the right local conditions and prescribe Galois actions. So this came up a bit in the last talk. It's going to be one of our main focuses, right, is being able to control these local conditions and the Galois conditions. And then we can use class field theory to finish the loop. So I really liked Mazur's. Mazur does a much better job of outlining circles, so you can go read in the paper. But I think it gives a really nice way to frame how all of these ideas fit together. So from these 6 facets, we could go in a number of different directions. And so what I want to focus on in the talk today are boxes 3, 4, 5, and 6. So we sort of fit exactly in the complement of the assumptions that Patrick used, right? We want to be in the residually reducible case. We want to be thinking about congruences between new forms and Eisenstein series. So that's boxes 3 and 4. And then when we talk about these R equal T theorems, T is going to be something that parameterizes our Cuss form. So T will be associated to box 4, and R will be associated to box 5. And then we're going to use some cool Kummer theory to construct abelian extensions, which will tell us about some of the beautiful arithmetic that's showing up. All right. Okay, so now we're going to jump into Eisenstein congruences. And so my plan is to go through a review of what happens in the prime level case, and then we'll jump into a more specific, the explicit setting that we'll use this rank bounding for. So let's consider the following setup. We'll let P be a prime at least 5, and N is another prime. So we want to consider classical weight 2 modular forms of level gamma naught 0. Sound good? All right, and so we have one Eisenstein series of level gamma naught N, which I've written here. So this E2 is our level 1 Eisenstein series, whose constant term is related to our Bernoulli number. And then we can consider this Hecke action on our modular forms that Patrick mentioned. And so we're going to consider the annihilator of the Eisenstein series. So if I wrote out the Q expansion of this Eisenstein series, we'd see that for primes L, the coefficient, the L Fourier coefficient is L plus 1. So we take our Lth Hecke operator and subtract off L minus 1, and those operators will annihilate this Eisenstein series. Good? Okay. And then we're going to take our Hecke algebra, and we want to complete it at the maximal ideal generated by P and our annihilator of the Eisenstein ideal. And then we can restrict our action to just our Cuss forms, and we can look at the image of this annihilator. So in terms of terminology, I0, the last line, we call this the Eisenstein ideal. And I want to point out that one kind of technical detail I won't talk too much about is that I'm staying away from our ramified Hecke operators here, right? So because we're at prime level, we just need to consider our nice TL operators. I don't need to think about UL or Achenleiner. Okay, so in this setup, we have this paper of Mazur, which also turned 50. It was a dual birthday party. And so Mazur says that if we assume P is distinct from N, then the following 3 statements hold. So 1, the cuspidal quotient of our Hecke algebra is not 0 if and only if P divides the numerator of N minus 1 over 12, which is very easy to check, right? Okay, and so what does it mean for this cuspidal quotient to be non-zero? That means there is an Eisenstein congruence existing. So I could have phrased it that way instead, that there is a modular, a Cuss form of level N that's congruent to our Eisenstein series. So the second statement is that this Hecke algebra is Gorenstein, which is a geometric property. We won't get too far into it. Basically, what you should think of, it's a nice geometric property that's closely related to being able to use this Weil's numerical criterion. So we'll talk about that in a moment. And then the third statement says that this Eisenstein ideal is principal, and that it's generated by any TL minus L minus 1, well, if and only if L is not 1 mod P and L is not a Pth power mod N. So this, oh, is there a laser? Yeah, there's a laser. This L is not a Pth power mod N. Mazur says that this is a good prime. So we can think of it, we're saying TL minus L minus 1 generates the Eisenstein ideal if and only if Mazur is if it's a good prime. Okay. All right. So I said number 1 is telling us from number 1 we know that there is an Eisenstein congruence existing in the situation, but we can say a bit more. We can actually show that this cuspidal Hecke algebra is free over ZP, and it has rank at least 1. So Mazur asked in his question, well, can we say more about the rank, right? So we know the rank as a ZP module is at least 1. Can we distinguish between when it's strictly greater than 1 and exactly equal to 1? And so the distinguishing here, right, we're saying, can we have an arithmetic condition that detects when the rank is minimal? So we're not necessarily distinguishing between higher rank cases, but can we tell when it's minimal? And this question's been studied by a variety of different people. So here's a selection, not exhaustive, of these types of results. So first, in 96, Morel proved that the ZP rank of our cuspidal Hecke algebra is not minimal if and only if this product of I to the I, and we're just working here, mod n. So is it Pth power mod n? So it kind of looks funny, right? This is called Morell's number. It's also I guess with the arithmetic conditions, they're very pleasing when you can compute them very easily, right? We can just check if it's a p power. So this is known as Morell's number. It's a very deep result. There's another formulation that's equivalent in terms of the order vanishing of a zeta value, which I won't go into. So that's one flavor. Then in 2005, Caligari-Emerton proved this is one direction. So this is saying if the cuspidal quotient has non-minimal rank, so there's at least 2 cusp forms that are congruent to our Eisenstein series, then the FP dimension of the P part of the class group, where we adjoin the Pth root of n, is strictly greater than 1. And we can also phrase this in terms of cyclicity condition, right? We're saying that the P part of this class group is not cyclic. Okay, so that's a completely different flavor of result. And another completely different flavor of result from Wake-Walk-Erickson in 2020 says that the rank is non-minimal if and only if some cup product in Galois cohomology vanishes. And so I like to, part of why I picked these 3 results is I like to give an idea of kind of the wide variety of arithmetic conditions that can pop up in this setting. And so the relationship between these are very intricate. So there are other class group statements we could make. And since I didn't put it up, I probably should have kept this comment in my head. But there are many different cup products floating around. And when you change the cup product slightly, then they'll correspond to slightly different class group statements. Okay? And so the main difference I should point out now is that in terms of the tools for proving this, 1 is fundamentally different than 2 and 3. So 1 is proven by computing directly on the T side using modular symbols, which, did those come up in the computational course or no? No? Okay. So they're a very interesting tool for computing with modular forms. And on the other hand, 2 and 3 both come from one of these R equal T theorems. So in order to argue 2 or 3, you need to prove R equal T first, and then you leverage the relationship between these objects to deduce something about the arithmetic. So they're very different flavors. And so our perspective today is going to be to focus on Wake-Walk-Erickson's perspective, where we're looking towards Galois cohomology as our source of arithmetic. Good? Okay, so I wanted to give a little outline. We keep saying this R equal T business. What do we mean when we say an R equal T theorem? And so this is also known as a modularity theorem. And so I like to think about this type of result in terms of 3 parts. So first we have our R part, which we already said corresponded to box 5, I believe, right? So this information parameterizes information about Galois representations that satisfy certain local conditions. So you set up a deformation problem with certain conditions, and then you want to parameterize any, the family of Galois representations that you obtain. The second object here is our Hecke algebra, which is acting on our space of modular forms. So it's also parameterizing some information about our modular forms. And the third part is, does this information match? So I like to emphasize thinking about them all separately because each part takes a lot to understand, right? So the starting point of, not the starting point, but a big technical part of Carl and Preston's work is constructing this R object, right? So I'm just trying to make the point that there are many steps before we get to the equals part, right? Understanding the construction of each. Okay, so assuming that we have our R and a T, how do we try to get to the dotted lines? Well, there's a standard argument for how to construct a surjection from R to T. Okay, so that direction is not a problem. But to conclude equality, in both the Caligari-Emerton and Wake-Walk-Erickson, they use Weyl's numerical criterion. So the numerical criterion is, you can think about it as being related to the constant term of these Eisenstein series. So it's showing the size of a certain quotient is what you expect it to be. But the important thing to note is that in order to use Weyl's numerical criterion, you really need your Hecke algebra to be a local complete intersection. And I put it requires T, but it's even more than that. It's like really if and only if. So you can only hope to use this strategy if your Hecke algebra is nice in a geometric way. So although I won't talk about it today, Carl Carl and Preston applied this strategy in lots of other square-free cases. So I'm only talking about prime level, but they figure out, or they apply it in lots of other square-free cases. But the key point with their previous work, before what I'm talking about today, is that in every setting, they need this nice geometric property to hold. So what's our goal for today? Oh, that's the volume. The goal for today is to outline a completely new approach. We're going to throw the numerical criterion out the window for counting the rank of R directly when our Hecke algebra is not LCI. So there's a couple of novel aspects of the project. So the starting point is the same surjection here, R to T. So we use the same R, which I'll talk about in a moment, that Carl and Preston constructed, and we're starting from the same R surjects onto T. The point here is that we're going to give conditions in a variety of different formulations that will control the rank of R. So if we can force R to be small, it's going to force an isomorphism. So that's what I mean by rank bounding. And so I'll try to highlight it as I go throughout, but part of the novelty is computing directly on the R side. At least as far as we know, I think this was one of the first attempts to really compute on the R side, or what you could imagine to mean to compute on the R side. So the long-term goal, which I certainly will not see the end of, would be to show that this is the correct R for any square-free level of level gamma naught n, right? And so what this project did is we tried to do a test case for the smallest setting where the numerical criterion fails. And you'll see the computation, the arithmetic gets out of hand quickly. So we'll have to kind of understand what's going on in a big picture way before we can hope to generalize it to other square-free level. Okay. Questions before I go on? Yeah. Oh, I think that I don't know that I can answer it too specifically, but I think that Carl and Preston's original strategy is it's closely related with Caligari-Emerton. So they both fall into this category of applying Weil's numerical criterion. So I guess like the setup is similar, but once we're trying to show the R equal T part, it's completely different. Yeah, okay. I guess I shouldn't say completely, because I'm not going to formulate it this way today, but you can make, statements about class groups as well from our approach. But does that answer your question? Yeah, okay. All right, so what's our setup? So I'm going to refer to this setup as Ribot's new form setting, which I'll explain why in a moment. And so this is a setting we'll be in for the rest of the talk. All right, so what's our setup? Well, we want to consider, so P is a prime that's still at least 5, and we want to consider N to be square free, the product of exactly 2 primes, and we want the following conditions to be satisfied. So first we need L naught to be 1 mod P. Does anyone see why we want that condition? This is where I test if you're awake. I see we're sleeping. Okay, we're shy. So we want L naught to be 1 mod P to put us in the Eisenstein case, right? Think back to Mazur's original result, bless you, that we want an Eisenstein congruence to exist. So L naught being congruent to 1 mod P is going to give us a first Eisenstein congruence with our Eisenstein series. And then we want the ZP rank of that Hecke algebra of level L naught to be exactly 1. So this second condition is a choice we're making to just make our lives nice, right? So if we want to generalize, the first thing that would go is this, right? That's just to keep our rank as small as possible to start. We don't want extra congruences floating around. And in particular, like Morel's number is a really nice way to implement this condition, right? We can just check very quickly, is it met or not? So that's L naught. We can think of L naught as being 1 mod P, and we don't have any extra Eisenstein congruences floating around. And then the second prime, we want it to not be plus or minus 1 mod P, but we do want it to be a Pth power mod L naught. So this is the condition. This is a Mazur bad prime. So we want to pick a Mazur bad prime, pair it with this L naught. And the reason for this condition, oh, sorry, I got ahead of myself. All right, so these are our 2 primes. Since we have 2 primes, our Eisenstein space will be spanned by 3 Eisenstein series. And so to single one out, we're going to fix our Akin-Lehner signature to be -1, -1. So The Akin-Lehner involutions are another type of Hecke operator that acts on our space of modular forms. And so we're going to pick the eigenvalues to be -1 and -1. The eigenvalues are either plus or -1, and that will single out a single Eisenstein series for us. All right. And so now the reason why we want the Maser bad prime condition is that this is a surprise, right? That when you have these assumptions, Ribbit proves that there's actually another new form. So there's a new form of level n that satisfies an Eisenstein congruence mod p. So this is an example. We might call this a level raising congruence because there's a congruence between a form of level L naught and then this form of level n. And so I think this can, at least for me, this condition that L1 is a p power mod L is a surprising way to detect that this extra congruence exists. Okay. So this is why we call it the Ribbit new form setting. This is Ribbit's new form. And so this tells us that the rank of T, the ZP rank of T is at least 3. And this is not the cuspidal part. This is just the whole Hecke algebra. And that's because we have one Eisenstein series. We have one cusp form of level L naught. And we have one new form of level n. Make sense? OK, and then we can check computationally that the Hecke algebra is not a local complete intersection. So you can do this. I believe it's called the Gorenstein defect. So there's like a quick computational way to show it's not Gorenstein, which means it's not LCI. So this is putting us in a situation where we cannot use the previous strategy. All right. OK, so we're actually ready to just state our main result. And I'm going to state the main result in a few different languages. That's kind of like the rest of the talk. We'll go on a tour of the different languages for the, yeah.
Could you say what you mean by the level raising?
Oh. So I didn't name the form here. This form comes from level L naught. So it's a new form of level L naught. And so we're saying that there's a congruence between this form of level L naught and this is new at level n. Does that make sense? It's because remember this is originally congruent to the Eisenstein series. There's only one residual Q expansion. Does that make sense? You can think of it either way. I believe or at least I think the level raising would apply in either case. Yeah. Good? All right, so the main result we're going to start with is in terms of algebraic number theory. I think that's usually the nicest way to start. And we're going to build a tower of P extensions of Q adjoint zeta P. So I think maybe you haven't, in the mini course, you maybe didn't see like this level of specification with our tower, but it's a similar idea where we're constructing these Galois extensions on top of one another. Okay, so let's start. This is always my favorite slide. When I don't really like Beamer talks too much, but this is my favorite one when I do give them, because we get to build our tower. So where's our starting point of the tower? So the basement here, we just adjoin our P root of unity, and then we have our K and our L. So K, we can write down a nice explicit formula for. We adjoin the P root of unity and a P root of L1. That's K, and so you should think that K is associated to L1. And then L, we cannot write down such a nice close form for it, but it's defined kind of intrinsically from your choice at L naught. So it's ramified only at L naught, things like that. And then we can take their composite, and that we'll call M. All right, next level. Oops, I went the wrong way. OK, so our next level, so now each line that you see in the diagram is degree P with prescribed Galois group you'll see as we go up the tower. So what's our next level? So we want M prime over Q to be Galois. It won't be abelian, but just Galois over Q. And then we want M prime over M to be omega not isotypic, where remember omega is our mod P cyclotomic character. And so this is another thing that Patrick explained so nicely, that this is just saying what the Galois action should be, the Galois action of the Galois group of Q adjoint zeta P over Q. It should act on this degree P extension in a certain way. And it should also be unramified, so no ramification. And then we also insist that the primes over L naught split in M prime over M. Good? Okay, so these conditions uniquely pick out this M prime. And then we go one more level up. M double prime. And so M double prime may or may not exist a priori. So you have to be a little bit more careful. M double prime, when it exists, is characterized by a similar set of conditions. So it too is Galois over Q. It also has a prescribed Galois action coming from the Galois group of the cyclotomic group, the Q adjoins zeta P over Q, and it has a condition on its conductor. And again, we want primes over L naught to split in M double prime over M prime. Okay, so I could state the main result in terms of M prime and M double prime, but remember our goal is to compute these number fields. And so that seems rough. So instead, we're going to be able to cut out smaller number fields K prime and K double prime that correspond to M prime and M double prime. Oh, sorry, yeah. Oh, because the arrows correspond to containment. So that's a great question. So K prime and K double prime, neither contains the other. So K prime is contained in M prime. M double prime contains M single prime, but you don't have containment with. Does that answer your question? Very good. Yeah.
So how is K double prime defined?
We'll get to that. Yeah. But the key feature that you should keep in mind is that M prime and M double prime are more like canonically defined. They're not based on any choices. K prime and K double prime, they depend heavily on choices that you make. So that's the next slide. Yeah? Yep. Oh, I didn't say it. It's a conductor. The conductor should be like the product of primes over P, like P squared for all the primes over P and M double prime over M prime. Something like that. Yep, okay. All right, so here's the result in terms of K prime and K. For P, so for a triple P, L naught, L1 that satisfy our Ribet-New form assumptions, if the Hecke rank is non-minimal, so if it is at least 4, then the following conditions hold. So 1, all primes of K over L1, they split in K prime over K. And secondly, there exists a prime of K over L naught that splits in both of these K prime and K double prime. Does that make sense? Great. And so the point here is that if either condition fails, then we get a surjection. Our surjection from R onto T, it becomes an isomorphism. So you'll notice this is similar to the Caligari-Emerton result where we're only getting one direction, right? We're only getting that if the rank of T is non-minimal, then we have these conditions coming from our tower. But that makes sense because our strategy is to force the rank of R to be small. And so we won't get an isomorphism automatically if the rank of these objects is big. Yeah.
You said K prime and K double prime depend on choices. Does condition 2 depend on those choices?
No, they don't. So, okay, you guys are jumping ahead. So it's okay, that's good. That usually indicates listening. So in a second, we're going to translate these into conditions on the Galois cohomology side. And so the point is that you make a lot of choices when you're selecting like cocycles and cochains. But at the end of the day, condition 2 is going to be about, it's going to be about an invariant vanishing. And whether or not it vanishes is independent of the choices of the pinning data. We call it the pinning data. Yeah. Other questions? Okay, so I always like to give us a little bit of a break before we go into the Galois cohomology, which is to talk about the computation, right? So the whole goal of this project, like, I guess when we started to work on it, it seemed like for it to pass as a test case, we needed to be able to compute these things, right? It's not really interesting if we can't check if the conditions hold at all. And so we attempted to verify the conditions 1 and 2 for triples in the following ranges. So for P equals 5 and P equals 7, so for P equals 5, we let L naught go up to 100 and L1 go up to 1,000. And then for P equals 7, we let L naught go up to 50 and L1 go up to 500. And so to summarize, we found that every example for which our algorithm completed, it's consistent with the conjecture that R should be equal to T, regardless of whether it's minimal or non-minimal rank. So specifically, we found one of two things. We found that either the second condition is not satisfied, forcing r equals t, and then we know it's that r is equal to t, or we compute that both of our conditions are satisfied, and we independently compute using modular symbols that the Hecker rank is also non-minimal. So we're not showing that, we can't show for sure that r equal t, but we're showing that they're both non-minimal at least, right? We'd have to play a similar game to then distinguish between 4 and 5 if we wanted to show equality here. So I'll come back at the end. There's a fun little, I'll make some fun little comments about this condition 2 verse 1, which can break at the end. Okay, and so in terms of data, so ignore the middle of the table for now. So these are some examples of ribbit new form triples. And then these are the conclusions. Is condition 2 satisfied? And then the matching Hecker rank. So that's just illustrating. If you see no, you see 3. If you see yes, you see the Hecker ranks at least 4. Okay. All right, I'm going to have to speed up a little. I'm going really slowly. I'm over at 12:15, right? I don't know how this happened. Yeah. Oh, the clock's fast. Oh, I was like, okay, great. Okay, so, sorry, I can take a breath. I was like, I don't know how this happened. Yeah, no, this is perfect. Okay, sorry, I had a little panic. All right, so now we're going to get a little bit more into the deformation theory, although I'm still going to skirt a lot of it under the rug, right? I kind of had to make a choice today about whether we wanted to talk about the deformation theory or the computation, and I picked the computation, but if you want to talk about the deformation theory, I'm happy to. So what I'll say is that I mentioned that when you're constructing this type of R, right, it's cut out by local conditions. So in our deformation problem, there's 4 conditions that we need. We want our representations to be unramified away from NP. There's a finite flat condition at P. We want the determinant to be cyclotomic, which corresponds to the fact that we're working with weight 2 modular forms. And then there's this condition called the unramified or Steinberg condition. And that is a condition that Carl and Preston formulated that should match the gamma naught level of modular form side. So that's our deformation problem. And so what I did instead of going through, I'm going to try to just boil down the input for this machinery. So the input for the deformation side are the following. So keep in mind the picture where we had these number fields K and L corresponding to our primes L0, L1. Same thing's going to happen on the Galois cohomology side. So if we start with a triple that satisfy our ribbit new form assumptions, then we fix 2 cocycles. So we have B1, which is the Kummer class of L1. So that is related to the L field. And then we have C1, which is a non-trivial class in the cohomology group that is characterized by L0, same as with our field K. Okay, so what do we do with these 2 cocycles? Well, this is, for number 2, this is where the Mazur bad prime comes in. So because L1 is a Mazur bad prime, mod L0, we can reformulate it as saying that this cup product in cohomology vanishes. But what that means in terms of looking at the cochain level is that there is a cochain A1 that satisfies this boundary equation, right? So vanishing in cohomology corresponds to being able to write down a solution for this equation. Okay, and then we keep going. Now we want to check for a similar, so now we want to check for this cochain B2 that satisfies our boundary equation here. So what I'm leaving out here, it's related to, it also came up in Patrick's talk about this tangent space business. So if you're wondering about the naming convention of these objects, they fit together into a matrix. So this A, B, C, D, they're really coefficients of a matrix that we can write down. It's related to the tangent space of this deformation ring, right? So this is what we're skirting under the rug. But what you should extract is like, we're looking for special cochains A1 and B2. So the 1 corresponds to, that's the data of a first order deformation, and B2 is the data of a second order deformation. And so the main result in terms of the deformation theory is that the FP dimension of R mod P is strictly greater than 3, if and only if. So when we evaluate this cochain at the Frobenius element L1, it vanishes. And a special invariant, which we call alpha squared plus beta, also vanishes. So this goes back to Ravi's question, right? That these choices are all dependent on pinning down your choices of these starting co-cycles. But what is independent is whether these objects vanish or not. So the vanishing is independent. Okay. All right, so how do we go from theory to computation? Well, and I guess I might have to go a little quickly through the end here, so if you have questions, I'm very happy to talk about it afterwards. But the basic idea here is that, and this goes back to the earlier question as well about how we get K prime and K double prime, this is how. So the idea here is that if we restrict these cochains to our field K, right, then we should be able to write down S units that correspond to, that give an extension corresponding to the restriction of these cochains. And so the idea here is that I wrote down these differential equations for A1 and B2. We want to think of it as an actual boundary problem, right? So if you're working in physics and you're thinking about a boundary problem, right? You first look for a general solution that satisfies your boundary equations, and then you adjust it to meet your, what do they call in physics? The edge conditions, right? Your local conditions. So we'll do the same thing here. So we want to find some candidate cochains that solve our different equations, differential equations, and then we want to make adjustments. So the diagram here, right, is that we could build this tower off of K or L, but we're going to work over K here. So we take our extension here, and then we're looking for S units that will generate these degree P Kummer extensions. And so if we assume that we have found these S units, then you see the conditions match up exactly, right, about these primes splitting in K prime over K, or K prime and K double prime over K, and these deformation theory invariants. So you get an exact matching. And I want to point out that on the deformation theory side, let me go back for a second. We're not missing a direction, right? On the deformation theory side, these arithmetic conditions exactly control whether or not we're having the minimal FP dimension here. Okay, and so with the last few minutes, I want to talk about how do we actually compute these S units. This was, I think, one of the most exciting moments when we were working on this project, was realizing how to compute these S units. And there's a really beautiful theory. So it comes from viewing our cup products in a different way. So instead of viewing them in terms of Galois cohomology, we want to view them as obstructions to lifting like a three-dimensional homomorphism where we forget about this top entry to a true homomorphism where we include the top entry. So if we forget this top entry and we just go off of our choice of B1 and C1, then for every A1 that satisfies this boundary equation, we'll get a true homomorphism here from GQ into GL3FP. Okay, and in particular, the homomorphism that we get, it's going to cut out a degree P cubed times P minus 1 extension of Q, and it has a prescribed Galois group. It's a twisted Heisenberg group. And these have been very carefully studied. And so it was a very fun realization we had when we realized that Sharifi's theory, it gives a formula for exactly this S unit, right? So if you set it up really carefully, so we want to compute an S unit that gives us K1, right? Sharifi gives a formula for it. So this is exactly the type of twisted Heisenberg extension that he's studying in his thesis, in fact. And so the formula here you can see is a pretty easy formula in terms of elements in our Galois group. Just our Galois group of, and I'm forgetting right now, I think it's the Galois group of K over Q adjoins zeta P. That's right. And so the takeaway from this is that we get a nice implementable, computable formula, and it's very nice. So there are still other conditions that I'm sweeping under the rug. Like here, we have like the local adjustments we have to make to meet all of the corresponding conditions coming from our deformation problem. But the takeaway is that we can compute this very nicely. And then when we go to the second order, the B2, now we have a more complicated boundary equation here, right? And the similar game, it will give us a degree P to the 4 times P minus 1 twisted Heisenberg extension. And so the way you want to think about this is in terms of two overlapping order 3 matrices. That's kind of the key to applying a Sharifi formula. And so it turns out that the solution here, it's related to a triple Massey product, right? So you can read the triple Massey product off the diagonal. It's related to B1, C1, B1 as a Massey product. So you have to make choices here, right, with your defining system. But you get an almost equally nice formula for how to compute the S unit here. So in terms of this formula, I want to point out that it's dependent on our choice here, right? Like we're assuming we have already done our A1 computation, and then it has the same flavor of local adjustments, right? So in both cases, the adjustments we have to make are a Galois action condition, finite flatness, and a condition at L naught, coming from the unramified Steinberg. Okay? And so now, we go back to our table. So now I've explained more the middle part of this table, which these are the adjustments that we keep track of once we have our S units in play. And so I just wanted to point out in the table, this beta difficulty factor, this was something that tripped us up for a long time in the computations, is that they don't feature directly into the computations in terms of the output, but the ramification type of P and K, whether it's wild or tame, the behavior at P, it really affects how difficult the computations are to run in terms of runtime. So this was something that tripped us up for a while. So in terms of a few comments about the implementation in Sage, so we use Sage rather than Magma, and I'd be curious to hear from, our Magma experts where it is now. But when we were doing this in, I think it was in 2020 or 2021, starting the computations, John Cremona had recently implemented some S unit packages. So that's kind of why we went with Sage. But and we just computed the computations on the clusters both at Swarthmore and at Pitt. And like I said, the hardest part, we're getting these adjustments to work out correctly. And so we knew that if we get 23, 43, 67, 97 to all work simultaneously, then we had one. But it took many tries. Okay, and so I'll end with this little diagram that just shows you kind of how to picture the story that I have been trying to convey. And so if you look at P equals 5, L naught equals 11, L1 equals 23, then we trace through. So the first column, this is constructing our K prime. And the second column is constructing our K double prime. And so the first box, this just comes from our new form setting data. And then we can compute our candidates just using our Sharifi theory. That's the input for Sharifi theory. And then we can compute our adjustments here. And so what I wanted to end with by saying is just to allude briefly to some ongoing work with Carl Wang Erickson and Liche Pozzi, that computationally we found that this condition always holds, right? That it's always condition 2 that's the problem. And we really couldn't figure out why. And so we've been working on a project that looks at level gamma 1. And so it turns out if you look at congruences where you have level 1, so I'll write it on the board because I was getting mixed up. So we want to go to the congruence group where you allow, so you're still there. There we go. Right, so we allow level gamma 1 for our Eisenstein congruence prime. Then it's in progress that we believe that we can show that this condition should always hold, theoretically. And so really, we argue that this alpha squared plus beta should sort of play the role of Morel's number in this more complicated story, that is, you can control exactly when you're having minimal rank versus nominal rank. Okay, I'll stop there.